While you are reading these very words, trillions of carats of sparkling razor-sharp diamonds are plunging out of an alien sky. They do not float down gently like winter snowflakes on a quiet morning, but rip downward like heavy artillery through a glowing, superheated fog. Deep inside the crushing gravity of a distant world, black carbon gas is snapping apart and locking itself into solid, multifaceted crystal gems. Astronomers, using the most advanced orbital telescopes on Earth, have proven that this is not a myth or a movie trick, but an active reality happening right now. If you love exploring the most mind-bending mysteries of our cosmos through real science without any fake exaggeration, make sure you hit that subscribe button right now. Join our community of curious thinkers who want to uncover the deepest, strangest secrets hidden in the dark corners of space before anyone else. To really grasp how a planet can drop solid treasure from the clouds, we have to look back at how humans used to view the architecture of outer space. For hundreds of years, astronomers believed that every solar system in the universe followed the exact same basic blueprint as our own home system. We had small, rocky planets like Mercury, Venus, Earth, and Mars, hugging the warmth of the central sun, followed by a vast belt of barren asteroids. Farther out in the cold, dark depths drifted the giant gas worlds, Jupiter, Saturn, Uranus, and Neptune, wrapped in thick blankets of swirling vapor. Scientists assumed that every single star in the Milky Way galaxy was surrounded by this exact same neat, orderly, and predictable pattern of worlds. That comfortable, orderly picture was blown wide open in the middle of the 1990s when astronomers detected the very first exoplanet orbiting a sun-like star. Instead of finding familiar, well-behaved planets, researchers kept running into terrifying alien landscapes that shattered every rule in our traditional astronomy textbooks. They discovered massive gas giants larger than Jupiter, orbiting so close to their host stars that a full planetary year lasted only a few Earth days. They found worlds where the daytime temperatures were hot enough to vaporize solid steel, and dark planets where the clouds were made of melted rock and boiling lead. Our solar system was not the universal standard after all, but merely one quiet, gentle room in a colossal cosmic mansion filled with extreme environments. As technology improved, astronomers built increasingly sensitive space telescopes to scan thousands of light years across the interstellar void. Instruments like the Kepler Space Telescope, the Hubble Space Telescope, and the James Webb Space Telescope began measuring the light passing through alien atmospheres. When starlight passes through the outer gas layers of a distant planet, specific wavelengths of that light are absorbed by different chemical elements in the atmosphere. By studying the missing colors in that light spectrum, scientists can read the atmospheric composition of a distant world almost as easily as reading a printed label in a grocery store. Time after time, the data revealed something stunning. Millions of mid-sized planets across our galaxy are packed with massive amounts of carbon and simple hydrocarbon gases. The most common hydrocarbon floating in these massive atmospheres is methane gas, which is made of one single carbon atom bound tightly to 4 hydrogen atoms. On Earth, methane is a very familiar substance that rises from decomposing swamps, natural gas deposits trapped deep underground, and the digestive systems of livestock. Under the mild temperatures and gentle atmospheric pressure of our home planet, methane behaves as a light, invisible, and completely harmless gas that drifts into the air. When you take millions of tons of methane gas and drop it into the crushing gravitational field of a giant planet, the basic rules of chemistry change completely. A planet that weighs 10, 20, or 30 times more than Earth pulls down on its surrounding gas layers with an unbelievable amount of continuous physical force. Scientists began using powerful supercomputers to simulate what happens to ordinary hydrocarbon molecules when they are dragged deep into these superdense atmospheres. The computer simulations revealed a dramatic breakdown where the rising heat and crushing atmospheric weight literally ripped the methane molecules to pieces. The weak chemical bonds holding the carbon and hydrogen atoms together snap under the pressure, separating the mixture into light hydrogen gas and dense, free-floating carbon. Those isolated carbon atoms are squeezed so violently by the surrounding air that they have only one physical way to stabilize themselves against the relentless pressure. They are forced to lock tightly together into an extremely rigid, three-dimensional geometric lattice that creates the hardest natural mineral known to science, pure diamond. For several decades, this idea of diamond rain remained a brilliant mathematical theory that many cautious researchers treated with a healthy dose of scientific skepticism. Equations on a chalkboard and computer simulations are helpful, but the scientific community needed hard, experimental proof before accepting such an extreme idea as a fact. They needed to physically recreate the terrifying interior of an alien giant world inside a controlled laboratory to see if diamonds would actually crystallize out of ordinary gas. That historic breakthrough finally happened when an international team of physicists gathered at the SLAC National Accelerator Laboratory in the state of California. The researchers designed an ambitious experiment to mimic the exact conditions found thousands of miles beneath the upper clouds of a massive planet. Instead of using dangerous, compressed methane gas, they selected a common plastic material called polystyrene, which is made of the exact same ratio of carbon and hydrogen atoms. They mounted a microscopic slice of this plastic inside a heavy vacuum chamber and aimed the Lenic coherent light source, one of the most powerful X-ray lasers on Earth, directly at it. The goal was to hit the plastic sample with an ultra-short, ultra-intense pulse of energy to recreate the violent shock waves moving through a deep planetary atmosphere. When the laser fired, it delivered 2 massive shock waves into the plastic sample within a tiny fraction of a single millisecond. The first shock wave compressed the material under millions of pounds of pressure, while the second shock wave drove the temperature above 8,000 degrees Fahrenheit. High-speed X-ray cameras captured the molecular reaction in real time, recording atomic movements that occurred in less than a billionth of a second. As the researchers watched their monitors in the control room, the chemical bonds of the plastic shattered instantly, and microscopic diamonds formed before their very eyes. For the first time in human history, scientists had watched carbon atoms crystallize into genuine diamonds under simulated alien weather conditions. Could you ever have imagined that blasting a common piece of everyday plastic with a laser beam could produce real diamonds out of thin air? Let us know what you think about this wild laboratory test in the comments below, and tap that like button right now if you love watching modern science solve cosmic puzzles. Once the laboratory physics confirmed that diamond rain was entirely possible, astronomers turned their full attention to the night sky to find real planets undergoing this process. They focused their search on a vast, mysterious category of worlds known to astrophysics as mini-Neptunes and super-Earths. These intermediate planets are much larger than our rocky homeworld, but significantly smaller than the gas behemoth Jupiter, making up the most common type of planet in the galaxy. Because our own solar system does not have a mini-Neptune, astronomers have to look across light years of interstellar space to study how these strange hybrid worlds function. These worlds are wrapped in deep, dynamic envelopes of volatile gases that create the exact atmospheric pressure cookers needed to produce non-stop diamond storms. To picture what this looks like in reality, imagine descending directly through the upper clouds of one of these carbon-rich worlds floating in deep space. At the highest altitude, the atmosphere appears dark, hazy, and peaceful, filled with thick, churning storm clouds that look like towering walls of brown and orange smog. The temperature in these upper cloud decks is relatively cool, allowing methane and other hydrocarbon gases to float quietly across regions that span tens of thousands of miles. Deep atmospheric currents, driven by the intense heat radiating from the planetary core, slowly drag these massive carbon clouds downward into the darker, heavier layers below. As a cloud of methane sinks, the surrounding environment turns increasingly violent, dense, and suffocating with every single mile of descent. For every 100 miles you travel downward into the atmosphere, the surrounding air pressure multiplies at a terrifying rate. The gas becomes so compressed that it stops behaving like the light air we breathe on Earth and begins acting like a heavy, viscous fluid as thick as warm motor oil. The temperature rises past several thousand degrees Fahrenheit, causing the surrounding gas to glow with an eerie reddish-orange thermal radiation in the gloom. The floating methane molecules are subjected to continuous mechanical stress until the structural integrity of the chemical bonds fails completely. When the sinking gas cloud reaches a depth of several thousand miles, the pressure hits an astronomical milestone known as 100 gigapascals. To put that number into everyday terms, 100 gigapascals is more than 1 million times greater than the air pressure you feel standing on a beach at sea level on Earth. Under this colossal weight, the thermal energy tears the outer hydrogen atoms completely away from their central carbon anchors. The isolated carbon atoms are crushed together by the surrounding weight of the sky, forcing them to bond instantly into microscopic crystal seeds. These tiny diamond seeds act like grains of dust in an Earth thunderstorm, pulling in more free carbon atoms as they fall through the dense, glowing fog. As the crystal seeds continue their downward journey, they grow rapidly in size, transforming from microscopic specks into heavy, solid gemstones. Within hours of falling through the dense carbon haze, some of these crystals grow into stones the size of marbles, while others expand into massive boulders weighing hundreds of pounds. They plunge through the glowing, superheated sky in a relentless, blinding cascade, creating a storm unlike anything that could ever exist in our gentle corner of the solar system. Trillions of carats of pure, faceted crystal tumble through the dark air, sparkling brilliantly as they reflect the faint thermal glow of the lower atmosphere. This downpour is far from a quiet, sparkling display of falling jewelry drifting lazily onto a clean, polished surface. The atmosphere of a giant planet is powered by intense thermal convection currents that generate supersonic jet streams blowing at thousands of miles per hour. These howling winds catch the falling diamond boulders, slamming them into each other with tremendous kinetic force and generating blinding bursts of static electricity. The lower sky becomes an impenetrable, roaring blizzard of solid gemstone hail ripping through superheated hydrogen gas in total darkness. Any spacecraft or robotic probe built by human hands would be shredded into fine metal powder in a fraction of a second inside this diamond-filled tempest. What happens next at the bottom of this falling storm is even more astonishing than the crystal precipitation itself. Scientists originally wondered if these falling diamonds would simply pile up over billions of years, creating a colossal mountain range of solid treasure at the planetary center. Advanced computer simulations and high-pressure laser experiments soon revealed a far stranger reality waiting at the lower boundary of the atmosphere. As the diamonds plunge even deeper toward the planetary core, the temperature rises beyond 10,000 degrees Fahrenheit, which is hotter than the visible surface of our sun. Under this unbelievable heat, even the rigid, unbreakable crystal lattice of a pure diamond can no longer maintain its solid shape. The solid gemstone boulders begin to soften around their edges, turning slushy before melting completely into a free-flowing, glowing liquid. The falling rain empties into an enormous, planet-spanning ocean made entirely of superheated, electrically conductive liquid diamond. Floating across the surface of this boiling carbon sea are massive floating blocks of solid diamond drifting like crystal icebergs in a glowing alien ocean. The entire planet is essentially a closed thermodynamic engine that creates diamonds in the sky, rains them down, and melts them into a boiling core. Have you ever heard of an entire ocean made of liquid diamonds stretching for thousands of miles across the heart of an alien world? Drop a comment below with your reaction to this unbelievable discovery, and take a moment to subscribe so you can journey with us through more cosmic wonders. This mind-boggling process is not something that only takes place in distant, unreachable star systems located thousands of light years away from our planet. It is actively happening right now inside our very own solar system, right under our noses on our neighboring ice giants, Uranus and Neptune. When NASA's Voyager 2 spacecraft flew past Uranus in 1986 and Neptune in 1989, it captured iconic images of smooth, pale blue spheres floating in the void. For decades afterward, standard school textbooks described these two outer worlds as quiet, freezing, and largely inactive balls of slushy water ice, methane, and ammonia. Scientists long believed that the interiors of Uranus and Neptune were relatively simple and sluggish compared to the roaring, dynamic storm belts of Jupiter and Saturn. They assumed that the distinct blue and cyan colors of both planets were simply caused by trace amounts of methane gas in the upper air, absorbing red wavelengths of sunlight. When modern physicists applied the latest diamond crystallization formulas to the temperature and pressure profiles of Uranus and Neptune, the results were unmistakable. The internal layers of both neighboring planets possess the exact density, temperature, and carbon saturation needed to trigger heavy diamond downpours every single day. This realization suddenly solved a massive scientific mystery that had puzzled planetary astronomers for more than 35 years. When Voyager 2 measured the infrared radiation coming from Neptune, it discovered that the planet radiates 2.6 times more heat into space than it receives from the distant sun. Neptune sits nearly 3 billion miles away from our star, receiving only a tiny trickle of weak, freezing sunlight across the vast expanse of space. Yet, deep inside its swirling blue atmosphere, something was generating an enormous amount of unexpected internal warmth that standard planetary models could not explain. The newly discovered diamond rain provides the missing physical engine that powers Neptune's internal heat source from within. As trillions of tons of solid diamond crystals form in the upper atmosphere and fall toward the center, they generate friction against the surrounding gases. The gravitational potential energy of these falling stones is converted directly into thermal heat as they sink through thousands of miles of dense planetary material. This falling crystal engine generates continuous, massive heat from the inside out, driving the violent, dark storm systems and supersonic white clouds seen on Neptune's outer surface. On Uranus, the situation presents a slightly different puzzle that scientists are still actively working to unravel today. Even though Uranus is almost the exact same size and mass as Neptune, it radiates very little excess heat into surrounding space, appearing thermally quiet by comparison. Researchers believe that Uranus may have an unusual interior structure, perhaps caused by an ancient collision with a giant protoplanet billions of years ago. This catastrophic impact could have knocked Uranus permanently onto its side and disrupted its internal convection layers, creating a thermal barrier that traps its internal heat and slows down the settling of its diamond rain. The presence of dynamic liquid diamond oceans deep inside Uranus and Neptune could also solve the mystery of their bizarre, chaotic magnetic fields. Earth has a clean, stable magnetic field generated by the churning of molten iron in its core, aligning closely with its north and south rotational poles. Uranus and Neptune, however, possess chaotic, crooked magnetic fields that are tilted at sharp angles of up to 60 degrees from their rotational axes. These irregular magnetic fields do not even pass through the centers of the planets. suggesting they are generated in shallow, off-center oceans of electrically conductive liquid carbon. If NASA launched a robotic probe designed to dive directly into the atmosphere of Neptune to measure this diamond rain, would you watch the live stream? Tell us in the comments what you think that probe would see on its descent, and hit that like button to support real scientific storytelling. While Uranus and Neptune give us spectacular examples close to home, the wider galaxy contains worlds where carbon chemistry operates on a scale that defies human imagination. One of the most famous and extreme examples is an exoplanet cataloged by astronomers as 55 Cancri e, located about 40 light-years away in the constellation Cancer. This massive world is roughly twice the width of Earth, but it packs more than 8 times our planet's mass into its dense, compressed sphere. It orbits its parent star at a dangerously close distance, completing an entire orbit, meaning a full planetary year, in just under 18 hours. Because 55. Cancri e sits so close to its star, its surface is permanently baked to temperatures exceeding 4,000 degrees Fahrenheit. When astronomers used space telescopes to measure the chemical composition of the star and its surrounding system, they found high ratios of carbon compared to oxygen. In an oxygen-rich system like our own, rocks and minerals are made primarily of silicates, quartz, and iron oxides, which form the dirt and mountains we walk on every day. In a carbon-dominated system, the geology of a rocky planet is built out of entirely different materials, creating worlds made mostly of graphite and solid diamond. Scientists modeling the interior of 55 Cancri estimate that at least a third of the entire planet's mass could be composed of pure diamond. Instead of having a crust made of granite and basalt, this superdense world likely possesses a dark surface crust made of graphite and shimmering crystal sheets. Beneath that graphite crust lies a colossal planetary mantle composed of solid, compressed diamond thousands of miles thick. It is an entire planet that functions as a cosmic treasure chest, containing far more diamond than exists across the entire surface and interior of our home planet. An even more mind-bending object discovered by radio astronomers is a celestial body known as PSR J1719-1438b, often called the pulsar diamond world. This object has an extraordinary origin story that began when 2 massive stars orbited each other in a tight binary dance billions of years ago. One of the stars reached the end of its life, exploded in a violent supernova, and collapsed into an ultra-dense, rapidly spinning neutron star called a pulsar. The second star expanded into a giant star, and the nearby pulsar began greedily stripping away all of its outer hydrogen and helium layers with its intense gravitational pull. Over billions of years of cosmic theft, the companion star was stripped down until only its ultra-dense dead core of carbon and oxygen remained. The crushing gravity of the remaining core compressed the carbon atoms until the entire leftover husk crystallized into a single planet-sized diamond sphere. This world is slightly larger than Jupiter in terms of its total mass, but it is packed into a ball only 5 times wider than Earth. It shines in the dark void as a single titanic crystal, orbiting its dead host star every 2 hours while being blasted by intense beams of pulsar radiation. These extreme worlds prove that our universe is far more diverse and chemically creative than human scientists ever imagined a few decades ago. On Earth, diamonds are prized for their rarity and used in luxury jewelry because they must be mined from rare volcanic pipes buried deep within the crust. Across the wider expanse of the Milky Way, however, diamond is not a rare luxury, but a common structural mineral that builds entire celestial bodies. There's more diamond drifting through the skies and mantles of exoplanets than all the gold, silver, and precious stones ever held by human hands combined. Which of these extreme worlds sounds more fascinating to you? The sizzling diamond crust of 55 Cancri A, or the dead pulsar diamond sphere? Leave your choice down in the comments below, and do not forget to subscribe to our channel for more deep dives into the extremes of astrophysics. To unlock more secrets of these diamond-filled worlds, astronomers are currently turning to the James Webb Space Telescope and next-generation ground observatories. By looking at the infrared light emitted by distant exoplanets, Webb can identify the precise chemical signatures of exotic clouds high in their atmospheres. Recent observations have shown that diamond rain is just one example of the incredible and violent weather systems operating on distant worlds across space. Astronomers have found scorching gas giants where the clouds are made of liquid corundum, the exact mineral that forms rubies and sapphires on Earth. On these ultra-hot gas planets, daytime temperatures vaporize metals into gaseous clouds that get carried by supersonic winds to the cooler nighttime side of the world. When the vapor cools down on the dark side of the planet, it condenses into shimmering clouds that rain liquid rubies and sapphires straight from the sky. On other worlds, temperatures are so high that silicate rock vaporizes into the atmosphere, creating storms where clouds of molten glass drop sideways in torrential hurricanes. The sky on an exoplanet is not a simple blanket of quiet air, but an active chemical laboratory producing phenomena beyond our wildest dreams. Understanding how diamonds form inside giant planets also gives materials scientists on Earth valuable clues for manufacturing advanced technologies. The same high-pressure physics that creates diamond rain in space is now being used in terrestrial laboratories to create brand new super-hard materials. Scientists are learning how to synthesize diamond layers with atomic precision, creating ultra-durable semiconductors, quantum computing chips, and laser optics. By studying the crushing physics of Neptune and Uranus, researchers are discovering new ways to manipulate matter at the atomic level right here on Earth. Right now, space agencies around the world are preparing the next phase of robotic exploration to study these icy, diamond-bearing worlds up close. Both NASA and the European Space Agency have listed a flagship mission to the ice giants as one of their highest scientific priorities for the coming decades. These ambitious proposed missions would send an advanced orbiter to circle Uranus or Neptune, accompanied by a heavily shielded atmospheric drop probe. The drop probe would plunge directly into the upper cloud layers, measuring temperature, pressure, and chemical changes in real time as it descends toward the crushing depths. As the probe sinks through the clouds, its onboard mass spectrometers would directly sample the carbon molecules as they begin to break apart under pressure. The data gathered during those few precious hours of descent would finally confirm the exact altitude where diamond rain begins to form inside an ice giant. It would also give us clear answers about the exact size of the falling stones and whether a true liquid diamond ocean exists around the core. This information would help astronomers build much more accurate models for the thousands of mini-Neptune exoplanets being discovered around other stars. Before these future robotic spacecraft can reach Uranus or Neptune, they will have to travel across the solar system for more than a decade through deep space. Scientists on Earth are spending this waiting period refining their laboratory lasers and running larger supercomputer simulations to prepare for the data. Every new laser test brings us closer to understanding how carbon behaves under conditions that would crush an armored submarine into a flat metal plate. The story of diamond rain is an ongoing scientific adventure that is still being written by researchers working in laboratories and observatories worldwide right now. To make these future discoveries even more exciting, astrophysicists are developing brand new theoretical frameworks to study what happens to diamonds over billions of years. Inside giant planets, the intense heat and gravitational compression do not stay constant over the entire lifetime of a solar system. As a planet gradually cools down over eons, the depth at which diamonds can form slowly moves upward toward the visible atmosphere. This means that an older ice giant might experience diamond storms at much shallower depths than a young planet that is still hot from its initial formation. The weather on these giant worlds is not static, but slowly evolves across billions of years of cosmic history. Scientists are also discovering that other elements mixed into the atmosphere can change the color and quality of the falling diamond stones. If trace amounts of nitrogen gas are present when the carbon bonds snap, the diamonds can form with a rich yellow or golden tint inside their crystal lattice. If small traces of boron gas are caught in the downpour, the falling crystals turn an intense, glowing blue, identical to the rarest and most expensive diamonds found on Earth. Imagine standing beneath a storm where the sky is dropping millions of blue and yellow gemstones, flashing with color against the dark, alien clouds. These subtle chemical variations mean that every single carbon-rich world in our galaxy likely produces its own unique variety of gemstone weather. In addition to ice giants, researchers are examining how diamond formation might occur inside brown dwarfs, which are failed stars that sit between giant planets and true stars. Brown dwarfs are too small to ignite nuclear fusion in their cores, but they are significantly hotter and more massive than any planet in our solar system. In the upper atmospheres of brown dwarfs, temperatures and pressures reach the exact sweet spot where heavy carbon clouds can condense and form massive crystal showers. These failed stars could be continuously producing diamond storms on a scale that dwarfs anything seen inside a planet like Neptune or Uranus. The total amount of diamond locked inside brown dwarfs across the Milky Way could easily outweigh entire planetary systems. Have you ever wondered if there are entire brown dwarfs out there that act like giant diamond factories drifting silently between the stars? Drop a comment below with your thoughts on these failed stars, and make sure to subscribe so you never miss another deep space investigation. Astronomers are also designing new ground-based megatelescopes, such as the Extremely Large Telescope, currently being constructed in the Atacama Desert in Chile. With a primary mirror spanning 39 meters across, this massive observatory will be able to capture direct images of exoplanet atmospheres with unprecedented clarity. It will allow researchers to observe the light reflected from alien cloud decks and measure the precise size of aerosol particles floating in their skies. If a distant planet has clouds of diamond dust drifting through its upper atmosphere, The extremely large telescope will be able to detect the unique optical scattering pattern of crystal facets. We are standing on the very edge of an era where we will be able to watch alien diamond weather unfold in real time across the galaxy. The study of extreme planetary chemistry is also forcing scientists to rethink how we search for extraterrestrial life on other worlds. For a long time, astrobiologists assumed that life could only emerge on planets that closely resemble Earth in terms of water, rock, and mild atmospheric pressure. However, studying the complex carbon chemistry of diamond-forming planets shows that organic molecules can survive and interact in ways we never thought possible. While living organisms certainly could not survive in the crushing depths of a diamond rainstorm, the complex hydrocarbons in the upper atmosphere could form the building blocks for exotic life. The boundaries of where life might exist in the universe continue to expand with every new planetary discovery we make. Every time we discover a planet that rains diamonds or a world covered in liquid gems, it forces us to expand our understanding of what nature can create. The laws of physics and chemistry are universal, but when they are applied under extreme conditions of heat and pressure, they produce wonders that look like pure magic. From microscopic diamonds formed in California laser labs to giant crystal planets orbiting dead pulsars, the cosmos is filled with breathtaking phenomena waiting to be understood. Our journey of exploration is only just beginning, and the telescopes of tomorrow will undoubtedly reveal even more incredible worlds that defy our expectations. When we look up at the night sky and study these extreme gem-raining worlds, it gives us a deep and profound appreciation for our own planet Earth. Earth orbits our sun in a narrow, safe region where temperatures and pressures allow ordinary life-giving liquid water to fall gently from the sky. Our clouds are made of soft water droplets that nourish forests, fill rivers, and support a rich web of living creatures across every continent. While a sky that rains glittering diamonds sounds like a breathtaking fantasy, it is actually a terrifying environment of deadly pressure, heat, and violence. Every strange exoplanet we discover reminds us that our homeworld is a fragile, rare paradise floating in a violent and chaotic cosmos. We live on a peaceful, rocky sanctuary where the atmosphere protects us, while the rest of the universe is dominated by skies of fire, iron, and crushing crystal. Human curiosity drives us to look out across the dark void, build bigger telescopes, and push our understanding of nature to its absolute limits. As long as there are mysterious lights in the sky, we will keep searching for answers and discovering wonders that challenge everything we thought we knew. Thank you so much for joining us on this fascinating journey across the cosmos to explore the worlds that rain diamonds from the sky. If you enjoyed this deep dive, please make sure to subscribe to the channel, turn on the notification bell so you never miss an upload, and share this video with a friend who loves space science. Leave a comment below telling us what strange cosmic mystery you want us to investigate next, whether it is liquid iron rain, oceans of lava, or planets made of solid ice that burns. We truly appreciate your support and curiosity, and we cannot wait to see you next time as we explore another incredible secret of our vast and beautiful universe.